Welcome back to Topics in Statics. This time we're going to do a little bit of a review of cross products. This is all going to be mathematical, just to make sure everybody's on the same page and know how to calculate this. Cross product, or also called the vector product, is when I take two vectors, I multiply them together in such a way that the resultant is going to be another vector. This is inherently a three-dimensional thing. It only works in 3 dimensions. So I've got to have 3 components, x, y, and z components of each vector. The reason it's 3-dimensional is that the original 2 vectors that I'm going to multiply together, if I draw them tail to tail, they'll always define a plane. But the vector that I end up with, my cross product, is going to be perpendicular to that plane. Therefore, it has to be in 3 dimensions. So the magnitude of the cross product is just the magnitude of A times the magnitude of B times the sine of the angle between them. The direction of the cross product is always perpendicular to both A and B. So you can see in the picture that it points perpendicular to the plane defined by those 2 vectors. The way you figure out, there's 2 possibilities. You could rotate one of 2 ways around that. And it's given by the right-hand rule. You point the fingers of your right hand in the direction of the first vector, A, curl your fingers towards the second vector, B, and your thumb points in the direction of the cross product. That's sometimes a little hard to see, but that's how it works. All right, now let's back up. Let's look at this expression for the magnitude of the cross product, AB sine alpha, where alpha is the angle between the 2. So when the 2 vectors are parallel, the cross product is 0. Right? If the 2 vectors are parallel, the cross product is 0 always. When the 2 vectors are perpendicular, the cross product's a maximum because sine alpha will be 1. So if I just look at what is B times the sine of alpha, that's the component of B that's perpendicular to A. Or I could rearrange that expression a little bit and say, what's A sine alpha? That's the component of A that's perpendicular to B. So essentially what the cross product is saying is I'm taking the magnitude of one vector and multiplying it times the component of the other vector that's perpendicular to it. And that's what I get, that the resultant is going to be those 2 numbers multiplied together. This whole expression, AB sine alpha, is only useful if I know the magnitudes of A and B and if I know the angle between them. Right? It leaves us totally up in the air about how to determine the direction in terms of I, J, and K. So we need a better way to calculate it. A couple more properties of the cross product. It's anti-commutative. From what we just did, if you change the order of the product, you have to change the sign of the result. And so A cross B is minus B cross A. In a right-handed coordinate system, which is the only kind we use, the unit vectors give us I cross J is K, J cross K is I, and K cross I is J. I don't know how to get you to figure that out, but it's a cyclic permutation. I know that doesn't help. The derivative of the cross product is the same as the derivative of the product of 2 scalar functions. So this shows you how to calculate a derivative. It's right. You just have to distribute that derivative. So the derivative of A cross B is the derivative of A crossed with B plus A crossed with the derivative of B. So calculating the cross product. Typically the way I do this is I write it in a compact determinant form. What that means is I write it the way it's shown at the right. If I'm going to do A cross B, the first thing I do is write down my 3 unit vectors, I hat, J hat, K hat. Then I write the first vector in the cross product, components form, AX, AY, AZ. Then I write the second vector also in component form, BX, BY, BZ. Those 2 vertical bars on the outside of it, those are the symbol telling me to take a determinant of this. it's a matrix thing, that's what those two vertical bars mean. They say take the determinant of this matrix. Right? Cross products are always three-dimensional, but in order to calculate it, I use what's called a 2x2 determinant. And a 2x2 determinant I show down here is A, B, C, D. The 2x2 determinant is AD minus BC. In other words, I take these two and multiply them together, and then I subtract these two multiplied together. So how does that help me calculate a determinant? What all of this says is that what I need to do is pick one row and one column. I'm always going to use the top row, so I'm going to highlight that. And then I'm going to pick a column, and so I highlight that. So there's the row and the column I want to use. So what I'm going to do is I'm going to write down that letter where those two intersect. So I'm in the I-hat direction. And then I take to the determinant of the stuff that's not crossed out. So that's this times this. So AY BZ minus AZ BY. Okay, that's the first term. So now I go back. I'm always going to take the top row. Now I take the middle column. So first thing I do is write down a letter where they intersect. And now I take this times this minus this times this. So AX BZ minus AZ BX. The trick here is if this first thing I wrote down, the J hat, has to be, I have to put a negative sign there. So now I got one more to do. So I'm going to take top row, take the top row, last column, I take where these two intersect, so I'm going to get plus K hat times this minus this. So AX BY minus AY BX. I know it's big and long and ugly. Can't help it. So there's your cross product, written out in all its gory details. You notice that if I interchange A and B, things change where their position. I get a minus sign essentially. But that's it. That's how you calculate a cross product. You need to work on that, get familiar with it. Next time we're going to come back and talk about a vector formulation of calculating moments using forces.